Swayam Prabha. Digital India. Educated India.
Yes, just roughly to tell what is going on. So there are, from the point of view of putting a barrier coating, they can have many different types of coatings. You can have electroplated coating sometimes to protect it from corrosion. You can have hot dip galvanizing, which Lakshman was also discussing yesterday, enameling, physical vapor deposition. All these are, everything produce different types of coatings, and that way you can protect it from corrosion. You see the electroplating, like the people do the chromium plating for reducing the corrosion problem. Where you have seen the chromium plating? Every day you must, probably some of you will be using it. Chromium plating for corrosion protection. Cap. Tap, yes. It's bicycle. That is the shiny bicycle handle is coated with chromium, right? So all these are having a chromium plating, and because chromium is itself is a less corrosive because of the chromium oxide, and that way it can protect. But again, the question is coming that if the chromium plating is good to use it, and everybody wants to replace the chromium plating, because chromium plating is, you need to use this kind of bath to get the chromium plating, which is not good to use. Hot dip galvanizing is a versatile coating for corrosion protection, which is also green in that way. It can be used still, and it is good to use. Everywhere you will see that, right? Lamppost and outside, if you take, or many applications you will see the galvanized steel. And anywhere else you see the car, right? The car body is made of galvanized steel to reduce the corrosion problem. This is what people are trying to replace with aluminum. Enameling is a glass coating, not so much for the corrosion protection that is used, although it gives a corrosion protection, but much more for the high temperature applications, like that's where it is used. Physical vapor deposition again is not directly for the corrosion process, but is much more for the wear applications, but it also, in added to that, it gives a corrosion protection. Thermal spraying is again for the high temperature applications. You can outside coating, you can make zirconium oxide and things like that by spraying with plasma, and so that this very high, otherwise high temperature melting oxide will melt, and it will be sprayed onto the surface, and then you can make a coating, and that is a very hard coating, and at the same corrosion protecting. Anodizing for aluminum is very much useful for corrosion protection again, but it's at the same time anodizing is not totally used for corrosion protection. It's also for decorative applications, but it also gives corrosion protection like that, right? Even sometimes the cladding is used for the corrosion protection. That means that you take if this is alloy, and you take a pure metal and clad it on the surface by rolling. Pure metal has a lower corrosion rate, and that way overall corrosion rate is decreased. Where this is used? Always we talk about that. The cladded material, where it is used? Not so much today, but earlier. In the aircraft. In the aircraft applications, when they use the aluminum copper alloy, its corrosion problem is, aluminum copper is not good from the corrosion point of view. Why they use it is, it's good from the point of view of strength, it is good from the point of view of fatigue. That's the reason that they use it. So in order to reduce the corrosion problem, they clad on the top with aluminum, pure aluminum. So this is called a cladded material, or duralumin. That's a trade name for that. Duralumin means it is this kind of cladded aluminum alloy. So all these are used for the corrosion protective applications. Some of them have the problem like chromium based coatings, which needs to be replaced, and so this is so it is less and less used chromium plating, but all other things are some or other way it is useful. But at the same time, one of the most used polymer coating is a polymer coating, right? The paint. And the paint, again, from the paint formulation side, there is a lot of things in relation with affecting the chemistry, this environment, and that's the reason that people are going more and more. For example, if you look at here, you can see that there is physically drying paint and chemically curing paint. If you look at this physically drying paint, which is old technology, And physically drying paint means all these physically drying paint has a solvent in it, and the solvent is evaporating, and then it is coming the whatever rubber, if there is a thing about the rubber, think that a paint is like a very fine rubber which is mixed in a organic solvent, acetone. So acetone will dissolve the rubber and forms a kind of an emulsion, and when it is painted, acetone will evaporate off and condense the rubber on the surface, and that way the coating. So that's the principle of, general principle of, we can say, the physically drying paints, but slowly, because of the green issue, this is moving towards chemically drying paints. Chemically drying paint means like you have the two component system more or less within the system, or one component can be just water, and there is a compound which in the paint, which together with water or another component react on the surface and form this bonding, and that way the coating is formed. So the advantage of that one is there is no evaporation of solvent in this case, because reaction is taking place within the system. So that way environment is it's not affecting the environment. And since it is not a solvent based systems, drying system, you can use water for that, because water molecules are inherently used within the system for forming the bonding. So water molecule disappear that way, excess water molecule will be evaporate, but otherwise it will be used in that way, and that way you can have this one. So companies like Hempel, this is one of the Danish company make, it's also international, there is part in India as well, I think it's in Pune, and so they make a very heavy duty paint for all applications like ship applications and different things, and they are moving more towards this chemically curing paint wherever it is possible like this. And then of course this paint is also functionalized. Functionalized means you can see that there is a zinc silicate in this paint, and zinc silicate is added because now, for example, when you have the paint on the top, when you have the zinc inside this paint itself will act as a sacrificial anode. Like this is equivalent to having the galvanization, for example, because the zinc is existing inside the paint. So it will act like a galvanized surface. People were using chromium earlier, and a chromium primer, which is available, chromium inhibited primer, but this is again replaced. Now nobody can use a chromium based paint, and everything is replaced with zinc and also other things. And again, this is not as good as chromium, but we have to live with it. That's more like that. People are also trying, instead of zinc these days, with graphene powder. Graphene is also like a very highly active surface, so people are also trying with add the graphene instead of zinc into this one, but none of them are into the commercial level. So that's what but everything is going towards this non-solvent based chemically drying paint, because that is at least somewhat green. But there are also research going on into making totally green, but finding out everything. That is, for example, if you are taking like if you take a paint, but I don't think that I wrote here, if you take a paint, there is binder in it, and there is then there is this molecule to give the color, and so there are many things inside the paint. So trying to find the replacement, green replacement for everything. This is also going on, that making a polymer technology, green inhibitors, what you can add, like I showed you the green inhibitors, raw materials like solvent and like that itself is using the raw materials like that. And so there is a lot of research going on in this area, but none of them is really commercial. The only thing what has happened over the years is that it is moved from the physically drying paint into the chemically curing paint. That's the situation today. Maybe these companies will work and try to make more green. There are research going on. There is research going on, and many people on the small samples, they show that it works, but nothing is commercial level. And that's also the case with the self-healing as well. This is another technology which people are trying, that is add something to the primer or the paint itself, and that will be kind of make it a kind of an active component when there is a problem. So that means that if you add these inhibitor molecules directly into the paint surface, it is mixed with the paint, it will not be probably easily coming out. But on the other hand, if this inhibitor molecule is added as a capsule into this, and if there is a crack here, this capsule also will break along with that crack, and that way the inhibitor molecule will be released into the crack, and then the crack is corrosion inhibited, like that. So with this kind of technology which is adding into the functionalized polymer, functionalizing the paint, there are many things going on. That is, there are some kind of chemistry you can add, where when you have the crack, that crack area will polymerize again, and that means almost like reforming the coating. So that kind of technology people are trying. Corrosion inhibitor, as I mentioned here, people are trying. Then they call it as reversible bond and things like that. This is a bit like here, that it reform the polymer. And so there are many things which people are trying, but again, nothing is commercial. At least I know that Europe, there is a company called AkzoNobel, and they are the one really trying to make it something commercial, but still it's not that simple. So it takes time, but there is driving towards the green technologies, using different chemicals in the paint, and also making the paint much more functionalized and that way more durable in this case. But again, that comes to the question that what kind of inhibitor you use. Is it imidazoline? Then maybe you can make the paint more durable, but it's not green. So there are many complex questions which they need to answer, and even regarding this. But whenever you have a paint also is another things which you need to look for, that is how to treat the substrate. So if you look at a paint layer, if you take the car and if you just take a cut on the paint, what you see is like this. You have the substrate, then there is about 1 micrometer of this, there is a layer, surface treated layer, which we call it as conversion coating, this part. Then you have the non-chromium primer, and then you have the top coat. This top coat is the one which is giving this appearance, and this is much more for the corrosion protection. We need this surface treatment, that is very important, because the surface treatment is the one which is giving the adhesion of the paint to the surface. Otherwise, paint will not adhere to the surface. If you take an aluminum surface and you paint it, after a few days when it is exposed to environment, you can peel off. So you need this adhesion promoter. And so that's the reason for the conversion coating, and adhesion is a key thing when you have a polymer coating. Because such kind of paint system, even if you take this whole thickness here is around 400 micrometer, 400 micrometer polymer thickness, if you calculate the diffusion of the moisture, it can get saturated with the moisture within few days. So that means that there is no meaning of saying that this will stop the water to go down. All polymers are permeable to moisture, and the moisture will go in. The only thing that stops the corrosion is that when the moisture is coming to the surface, if you cannot do the debonding, then you have the corrosion resistance. So the adhesion is a key thing, and that's the reason that this adhesion promoter here is a most important in the kind of paint structure. Again, coming to that, the most best treatment for this adhesion promoter here is this chromating. It's a very simple treatment. So that way, if you take this conversion coating process, what we are talking about is like this non-electrolytic type of conversion coating, where you take a metal surface, which dip it in a solution, you form a little bit of a very thin layer of around 100 to 500 nanometer. Not even 500 nanometer, actually I put in general with a different coating. If you take the chromating alone, maybe it's 100 nanometer. Layer of chromium oxide. So it's a very simple treatment. You take your metal surface, take a chromic acid solution, just dip it in that for some time, you have this coating. And this coating is a very good coating from the corrosion protective point of view. Chromium oxide is very good, right? From the self-healing point of view, it's very good, and it also gives a very good adhesion to the paint. And that way, this was one of the treatment which is people used for many years for the painting. And so you can also see this yellow color here. So this is before treatment. Yellow color is because of chromium oxide on the top. But again, the chromium oxide is carcinogenic, so it has to be replaced. The only place you can use the chromium-based coating is aerospace and defense, because there is much more safety is concerned. so that it is allowed to use a little bit more time, but all other places is phased out. So that means that people are trying with different technologies for making their conversion coating. What kind of technologies we can look at it? But again, thinking from that point of view, that's a chromium, right? Chromium is an oxidizing agent. Chromate is an oxidizing agent. So what chromate will do? Maybe I think I'll take this first, this slide, then we can go back. Yeah. What chromate will do is that you have the chromate solution here. Chromium is 6+ here. When you put it with the aluminum, chromium will oxidize aluminum and form aluminum oxide. Because chromium is an oxidizing agent, at the same time chromium is reduced into chromium 3. So you form the chromium 3 oxide, and while doing the chromium 3 oxide, that excess electron is given to the aluminum and form the aluminum oxide. So it's an oxidizing chemistry. It's just oxidize the surface. That's what happens. So you can also think in that manner. So that way, if you look at the conversion coating chemistry, which if you think from you want to produce from the green point of view, you can think that there are 3 conversion coating chemistry today. One is surface oxidation using an oxidizing agent like chromate, a compound formation on a surface using a chemistry. That means that directly something is attacking the surface and forming a chemistry. And third one is, which we saw earlier, cathode inhibition, where we can make a pH-based precipitation on the cathode, and that way you can make a coating. So this is the 3 technology which are going on, and so that way you can think about the replacement as well. And when you think about all these, nothing is as good as chromium even today. But coming back to this, so that means that if you are thinking about the oxide-based chemistries, you can think that instead of chromium, you can substitute that with the molybdenate. Molybdenum also works like chromium. So you can have the molybdenum as the chemistry as the oxidizing agent, and that way you could work. Permanganate is a good oxidizing agent. You can work with permanganate. Vanadate also can work. So people are working with molybdenate, permanganate, and vanadate. Among these 3, if you take, permanganate is the one which is already has a patented process. A Swedish company, they have a patented process which people can use permanganate, but all other things are in the developing stage. Phosphate coating is so much used, is another type which shall come, that is reacting with the surface. Then there is all the cerium and titanium and all those things. All these are precipitation type, where you are pH based. We will take one by one. This one I think I'll skip, because this one is just what Lakshman was showing yesterday with the patina formation, which is one of the key. Everywhere you go in Europe, you will see this. And this is becoming an important thing. We will take a little bit more of this tomorrow, because even this one is getting destroyed because of the acid rain. We'll come to that tomorrow rather than today. So this is also, Lakshman discussed about the weathering steel, which is used for the building us like that. We can form a patina, and that way this kind of iron steel is protected actually because of this patina formation. But why I put that one here is that this is exactly conversion coating. Like air is reacting with the surface, and air and water from the atmosphere is reacting with the surface and forming this coating, and this is exactly the meaning of the conversion coating. Part of the metal surface is converted. That's why it's called conversion coating. Anodizing is conversion coating because anodizing is formed from the material. When you do this treatment, also part of the metal is oxidized, so that's the reason that's calling conversion coating. And that's the reason I put here. Only difference is that all these patina formation takes many years. After 3 years, it is nothing. It takes many years, and when you're doing a conversion coating for an application, people will not wait for 3 years. They want to do it within 1 minute or 2 minutes. That's what they want. So that's a commercial process which people want to use it. So if you take these oxidizing chemistry-based coatings, you can, as I mentioned, that you can replace the chromium conversion coating with molybdenate, permanganate, and vanadate, because all these are, maybe I put it in a wrong way. I'll come to that. We also tried at DTU another type of conversion coating, which is a little bit like this anodic oxide coating, but we are using a just high temperature steam. High temperature steam to make the make a layer to act as a convection coating. So basically, it's the idea like you use a pressure cooker and cook it inside with a high pressure, and you have the high pressure steam. So if you take a normal pressure cooker, you can get instead of 100 degrees centigrade, you can get 135 degrees centigrade because of the higher pressure, where you form the steam with a 1.3 to 1.6 bar pressure, so slightly over pressured, and then you put the specimen, and because of the higher temperature and higher pressure, the water activity is higher. So that way you can change, for example, aluminum as an aluminum oxide, right? Always you have an aluminum oxide. What's the thickness of the aluminum oxide on a natural aluminum? What will be those? Maybe 3 to 4 nanometers. But 3 to nanometer oxide you can grow if you give a higher water activity on the surface. You can also do that with hot water. If you take a piece of aluminum in the hot water and just boil it, you thicken the aluminum oxide. But it takes, to get appreciable thickness, maybe it will take days, 10 days. Airbus was using in earlier, in some cases with boiling in water, but it takes 10 days probably to get an appreciable thickness. But in this case, when you increase the water activity, this aluminum oxide formation can be increased. You can do it by this kind of process. This is like a batch process. You have to put it inside the cooker, but you can also make a high pressure, high temperature steam, and then you can spray to the surface. So you get a similar effect as this one. And that way you can form the coating. So you get this kind of nice coating on the surface. This is the aluminum oxide, the only naturally formed aluminum oxide, we thickened into. You can see that with a steam treatment of 1.3 bar, we can go up to 600 nanometer thickness. With 1.3 bar, 600 nanometer, 1.6 bar is almost same. With 1.9 bar, we can go only up to 1 micrometer thickness. So you can make a thickness is not that important here. Even 600 nanometer or 300 nanometer is okay, but it forms the oxide and it also forms this rough structure. That's important. This nanoscale roughness is important because that will give a very good adhesion to the paint. Think that a paint is put on this. The paint adhesion is due to two factors. One is the chemical bonding. Another one is the mechanical locking. Mechanical locking, you need a rough surface. So this is good for that. Now coming to the chemical bonding, whenever you have an oxide on the surface, you have the OH groups. You have the OH groups projecting out. This OH group, hydroxyl group, will give a good bonding. So that way, both from the point of view of bonding as well as from the chemical locking, this is a good surface. Now take the kinetics part. You can see that this is 100 seconds. So that means that at least this 500 nanometer or 300 nanometer of the coating we can form within less than a minute. So that's a good process. That's a fast process for companies to use it. So that's also the advantage with that. So we did many studies in this, like so you can see that all these intermetallic particles are covering very well. So that's one other thing, right? These are the cathodic area. Intermetallic particle is covered very well. That's what also you see in this FIP cross section, which then, so you can see this interface here with this covering the intermetallic particles, which is covered very nicely with the coating like that. So all this cross section shows that if you take a cut here, it has a very good covering over the intermetallic particles. You can see that there is some special growth, right, over the intermetallic particles, because intermetallic particles contains iron as well. So it grows iron oxide and aluminum oxide. So you have this special growth on the intermetallic particle. It is covered. It is fully covered. The intermetallic particle, that way is good coating. I'm just jumping from one result to another. But you can see that all this coating works very well. So you can see that is with the cathodic reactivity is reduced so much. So this is without coating, and with coating cathodic reactivity is reduced at least 100 times. If you look at here, and you can also see that the anodic reactivity is reduced so much, maybe more than 4 decades. 10,000 times the anode reactivity is decreased. Not only that, it shows as a passive layer now, because it's a passive layer, right, with the oxide, and it is very difficult to break down. In this case, it shows a little bit breakdown, but otherwise it's very difficult to break down even with a very, very high voltage level. So that way it is looking at as a very nice coating to act as a conversion coating. But that's not enough. Commercial people will not accept with that result, because this is showing the taking the coated surface and putting in the solution, analyzing it and corrosion point of view. That's not enough. They want to see that whether with a paint it will work or not. So automotive industry comes, you can give all these results, just they throw away. What they want to know is that you take that coated surface, put a paint on the top. So take this surface, put a paint on the top. After putting the paint, you make a scratch on the paint, mimicking a crack formation on the paint. Then you put it into the salt spray testing, and then see that with the time for 1000 hours, 1000 hours, how much the corrosion is penetrating from the scratched area, how much it is penetrating. This is what they want to know. So then we did that. So you can take the reference with just a paint without any conversion coating, it immediately failed. But you can see here that is with this one, you have a much lower level of this filament level here, and so it is good. It's working good. I don't remember exactly what is the cutoff limit here, which they think, but I think it is coming somewhere later. But it is working, so that way it is having good adhesion. It is not allowing it to penetrate and the corrosion to occur. That's what you see here. And this is again showing that with you can also use different chemistry. Here we use just water, but you can also different chemistry you can use. You can use potassium permanganate chemistry and like that to increase the growth and things like that. But to summarize, that is, so here you can see that we did the actual experiment which the automotive industries want. For example, painted the surface, scratched the surface this way and this way, and then we exposed to the salt spray, and we are trying to see that how the filiform is, not salt spray. Here what we do is there is a specific testing for the filiform. You would scratch it this way, and then you put some hydrochloric acid, if I remember correctly, so that some chloride is introduced. Then you put it in a humidity chamber. In a humidity chamber, and humidity will make this chloride to penetrate and the corrosion to occur. Then you measure the filament length. That's what you see here. So when you do that, you can see that steam-based treatment, potassium permanganate and steam, nitric acid and steam, we can do many chemistries. And so that way you can see that all of them are showing within the limit. This is a limit. This is a standard which they want. The filament length has to be below 2 with that testing. So all of them was good with that from the point of view of our coating. But again, you can see one thing here. What do you see there? Now KMNO4 is bad. KMNO4 is bad. What another thing, what do you see there? Huh? Tell me. Yeah, exactly. Again, nothing to replace chromium. It's chromium is chromium. It is nothing to replace chromium. None of this coating is also come to that level of chromium coating, and that's what that's a fact. That's where we are. There is no technology to replace chromium today in the world. And if you can do a PhD in that and make a coating, conversion coating chemistry that can replace chromium, it will be really nice. And you can patent it, and you can make a lot of money out of that. But nothing is as good as chromium. We are trying to commercialize this as well, like the other coating. We are talking with the companies, like where they can use it and commercialize it, but still it is like not a very good replacement for chromium again. And from the mechanism point of view, just to tell that, why it works is that basically when you put the steam, and you can also use with a little bit of acidic chemistry. It's better to use a little bit of acidic chemistry in this. So into the water we add some a little bit of acid. Acid means again you can make it green. You can add lemon juice to make a pH a little bit lower. And then what happens is that you are playing with this boundary. So when the acidic solution is there, when the steam is more or less produced and a little bit of a spray, you have that acidic solution which will make the aluminum to dissolve more. when the aluminum is dissolving, this boundary is shifting here because the higher concentration of aluminum on the surface. Immediately that aluminum will be precipitated aluminum oxide. So we are playing with this boundary. If you use too much acid solution, you don't get this coating because then the aluminum will be dissolved. You need to play around this region to get a best coating, for example. So that's a mechanism at which we work in this. But there are, as I mentioned, that there are many other replacement. For example, another replacement is people are trying, especially in the automotive industry, is phosphate coating. Phosphate coating is quite simple coating because it is basically, if you put aluminum into the phosphate, it forms aluminum phosphate. There are many steps. Phosphate will react with the aluminum and form the aluminum phosphate on the surface. So that's it. So there are chemistries like this you can use if that react with the surface and forming a coating. So this is so much used in the automotive industry, and there is a reason that why it is also used in the automotive industry. That is, you can also form the similar type of coating on the zinc surface. Why it is interesting for the automotive industry? Huh? No. What I'm saying is, aluminum you can form. It can also form, the similar treatment can be used on the zinc surface as well. Why that is interesting? So zinc phosphate will form, like aluminum phosphate, it will form zinc phosphate. Why that is interesting? What's the material used for car today? Which one? You say steel? Yes, it's correct. But it is just steel? No, it is zinc coated with the zinc, and a steel coated with the zinc. The galvanized steel sheet, that's what is used for the car today because they want to reduce the corrosion problem. So the steel sheet is galvanized. So there is a thin layer of zinc on the top. So that means that you think that a car is made different parts. But some part is made of aluminum, some part is made of galvanized steel. Now the car has to go through the surface treatment. It will be very nice if they can have one process which can be useful for aluminum and steel together. That's what they can do with that. If they have to do it, one treatment for aluminum, then it has to go to the zinc treatment, then it's a very difficult thing. One can affect the other, and there are so many issues going to come. So whenever you have a multi-material car with aluminum and zinc together, and you can do it in one process with phosphating, and that's very good for them, and that's the reason that the automotive industry is very keen on using this. You can think about other replacement, which I mentioned about the oxide, right? We can use the permanganate and things like that for instead of chromium as an oxidizing chemistry. Another thing as a alternative for the chromium that is coming up is by using this thing which I mentioned in the beginning, this pH controlled precipitation. Earlier I mentioned this as an inhibition, but people are also now trying it as a coating. So that means that if you put this enough time, this in a cerium containing solution, for example, cerium hydroxide will form on the top, and then it slowly spread and form it as a little bit more of a coating. It will not cover the whole metal surface. Although I have shown is covering the whole metal surface, it will not cover the whole metal surface. Mostly the coating will be above the particles with a little bit also on the surface. That is another treatment people are trying. It is a pH based this mechanism. When you look at that point of view, you can have cerium, you can have titanium, because titanium also forms titanium hydroxide, right? All the material which is forming this one. That is what I want you to understand. You don't have to remember cerium and all those things. What you want to understand is the three technology where it is moving. One is moving towards looking into other oxidizing agent, which is as a replacement of chromium. Another one is something you can react with the surface like phosphate. The third thing is pH based mechanism. When you say pH mechanism, immediately you have to think that any element which has a Porbet diagram like this will work for it. Somebody was asking in the break to me that why people use lanthanum, yttrium, all these things for such kind of things, because if you look at the Porbet diagram for lanthanum, you will see the same thing. Yttrium, you will see the same thing. So that kind of material can be used. Everything that precipitates in the alkaline condition, that's important criteria for that. And I have also had because I think I messed up a little bit this here just moving the slides, I think. So from the molybdenate point of view, oxidation point of view, I told that molybdenum we can use or manganese you can use. But you can also look at this Porbel diagram and say this chromium, these are the elements near to the chromium which will have an oxidation capacity almost similar to chromium. So you can use manganese, you can use vanadium, molybdenum. People are also trying with the tungsten. So you can just see how I am trying to tailor. So that's the concept. That's the concept at which instead of chromium, whether we can use all this material. That's what people are trying as oxidizing chemistry. And similarly, I had a, yes. For this one, people are trying because now you can see that like titanium words, zirconium words, scandium, yttrium, lanthanum, cerium, lithium, all these are having Porbel diagram similar to what I shown here. So this is the way that people are thinking, the researchers are thinking and trying different things. Doesn't mean that all of them will work, but that's the way they are trying. From the concept that is that Porbel diagram, if you have, then you can make this pH control precipitation, and that way it can work as a coating. Out of this, the commercial process existing today is, there is a commercial process called titanium and zirconium together. So it's called titanium zirconium based coating. That's the only one that is commercial today. People are using it as a replacement chromium. Ask the question, is it worse like chromium? No. It is much worse than chromium still, but that is the alternative. So this is just showing that the mechanism of this chromium coating formation, the different steps in the reactions, the pH is changing locally, and then the cerium hydroxide will precipitate, and that is a sequence. It's just showing the sequence, otherwise nothing is much in this. So that's the last slide in that part. So you can, what I want to do is that, as I told you that, not to learn exact things what I mentioned and things like that, but you must have got an overall idea, right? Where the things are moving. Where the things are moving, or where we want to move, basically, and where we are stuck up. And I think if you get that overall flavor, I think that's enough. Is it okay? I'll stop here this part, and then I have to get into the other one. But any questions for this part?